Queries, keys, and values are terms that you will be using for attention. In this video, I will define them for you and show you how they could be used. Let's get started. The original attention paper was published in 2014. Since then, there have been multiple variations on attention, with some models that don't rely on recurrent neural networks. For example, the 2017 paper, Attention is All You Need, introduced the transformer model and a form of attention based on information retrieval using queries, keys, and values. This is an efficient and powerful form of attention that you'll be using in this week's assignment. In this video, I'll show you how this type of attention works, as well as the concept of alignment between languages. Conceptually, you can think of keys and values as a lookup table. The query is matched to a key, and the value associated with that key is returned. For example, if we are translating between French and English, l'heure matches with time, so we'd like to get the value for time. In practice, the queries, keys, and values are all represented by vectors, embedding vectors, for example. Due to this, you don't get exact matches, but the model can learn which words are the most similar between the source and target languages. This similarity between words is called alignment. The query and key vectors are used to calculate alignment scores that are measures of how well the query and keys match. These alignment scores are then turned into weights used for a weighted sum of the value vectors. This weighted sum of the value vectors is returned as the attention vector. This process can be performed using scaled dot product attention. The queries for each step are packed together into a matrix queue, so attention can be computed simultaneously for each query. The keys and values are also packed into matrices K and V. These matrices are the inputs for the attention function, shown as a diagram on the left and mathematically on the right. First, the queries and keys matrices are multiplied together to get a matrix of alignment scores. These are then scaled by the square root of the key vector dimension dk. This scaling improves the model performance for larger model sizes and could be seen as a regularization constant. Next, the scaled scores are converted to weights using the softmax function, such that the weights for each query sum to 1. Finally, the weight and the value matrices are multiplied to get the attention vectors for each query. You can think of the keys and the values as being the same. So when you multiply the softmax output with V, you are taking a linear combination of your initial input, which is then being fed to the decoder. Take a minute to make sure what I just said makes sense. Note that unlike the original form of attention, scaled dot product attention consists of only two matrix multiplications and no neural networks. Since matrix multiplication is highly optimized in modern deep learning frameworks, this form of attention is much faster to compute. But this also means that the alignments between the source and target languages must be learned elsewhere. Typically, alignment is learned in the input embeddings or in other linear layers before the attention layer. Before moving on, I want to look a bit closer at alignment. The alignment weights form a matrix with queries, target words on the rows, and keys, or source words, on the columns. Each entry in this matrix is the weight for the corresponding query key pair. Word pairs that have similar meanings, te and ti, for example, will have larger weights than dissimilar words like te and time. Through training, the model learns which words have similar meanings and encodes that information in the query and key vectors. Learning alignment like this is beneficial for translating between languages with different grammatical structures. Since attention looks at the entire input and target sentences at once and calculates alignments based on word pairs, weights are assigned appropriately regardless of word order. For example, in the sentence, the agreement on the European Economic Area was signed in August 1992, and this other sentence, l'accord sur la zone économique européenne a été signé en août 1992, you can see that zone and area are at different positions, but have the same meaning. The model has learned to align them appropriately, allowing the decoder to focus on the appropriate input words despite different ordering. Congrats on absorbing all these new concepts. I introduced you to the purpose of an attention layer. You saw how it is related with information retrieval, and I showed you how well it works even for languages with very different structures. In the next video, I'll be talking about neural machine translation and show you what the setup looks like for this system. I'll show you what the dataset looks like and the steps required for pre-processing your datasets.
You've now seen what keys, queries, and values are. These are important because if you read a research paper, you might come across these terms and you will understand them. In the next video, I will talk about the setup for machine translation. Welcome! I will now show you how to train a neural machine translation system from scratch. I'll go through every step slowly so you can understand what is going on behind the scenes. Let's get started.
In this video, I'll show you how everything you have seen this week fits together into the model architecture you'll implement in this week's assignment. First, I'll give you a general overview before I go into the more intricate details. You will implement a model similar to the one you have seen in previous lectures. You will have an encoder that gets the input sequence, a decoder, which is supposed to do the translation, and an attention mechanism, which would help the decoder focus on the important parts of the input sequence. Recall that the decoder is supposed to pass hidden states to the attention mechanism to get context vectors. The pass of the hidden states from the decoder to the attention mechanism could not be easy to implement. Instead, you'll be using two decoders, a pre-attention decoder to provide hidden states, and a post-attention decoder, which will provide the translation. So, a general overview of the modified model looks as follows. You will have the encoder and a pre-attention decoder that's got the input and target sequences. And then for the pre-attention decoder, the target sequence is shifted right, which is how you'll be implementing the teacher forcing. From the encoder and pre-attention decoder, you will retrieve the hidden states at each step and use them as input for the attention mechanism. You'll use the hidden states from the encoder as the keys and values, while those from the decoder are the queries. As you have seen in previous lectures, the attention mechanism will use these values to compute the context vectors. Finally, the post-attention decoder will use the context vectors as inputs to provide the predicted sequence. Now let's take a closer look at each piece of the model. The initial step is to make two copies of the input tokens and the target tokens because you'll need them in different places of the model. One copy of the input tokens is fed into the encoder, which is used to transform them into the key and value vectors, while a copy of the target tokens goes into the pre-attention decoder. Note that the computations done in the encoder and pre-attention decoder could be done in parallel since they don't depend on each other. Within the pre-attention decoder, you shift each sequence to the right and add a start of sentence token. In the encoder and pre-attention decoder, the inputs and targets go through an embedding layer before going through LSTMs. After getting the query key and value vectors, you have to prepare them for the attention layer. You'll use a function to help you get a padding mask to help the attention layer determine the padding tokens. This step is where you will use the copy of the input tokens. Now everything is ready for attention. You pass the queries, keys, values, and the mask to the attention layer that outputs the context vector and the mask. So before going through the decoder, you drop the mask. You then pass the context vectors through the decoder, composed of an LSTM, a dense layer, and a log softmax. In the end, your model returns log probabilities and a copy of the target tokens that you made at the beginning. There you have it, the model you'll be building and the intuition behind all the steps. Take a break and just let all that sink in.
You now have an overview of how NMT is implemented. If you did not understand everything, do not worry about it. We will go in more detail in this week's programming assignment. In the next video, I will talk about how to evaluate your system. Hello! You will now learn about two ways that will allow you to construct the translated sentence. The first approach is known as greedy decoding, and the second approach is known as random sampling. And you'll also see the pros and the cons of each method. For example, when choosing the word with the highest probability at every time step, that does not necessarily generate the best sequence. So with that said, let's dive in and explore these two methods.
By now, you have reached the final part of this week's lectures. That's awesome. I'll show you a few methods for sampling and decoding, as well as a discussion of an important hyperparameter in sampling called temperature. First, a quick reminder on how a seek-to-seek model predicts words. The output of the decoder is produced from a dense layer and a softmax or log softmax operation. The output at each step, then, is a probability distribution over all the words and symbols in the target's vocabulary. The final output of the model depends on how you choose the words using these probability distributions at each step. Greedy decoding is the simplest way to decode the model's predictions, as it selects the most probable word at every step. However, this approach has limitations. When you consider the highest probability for each prediction and concatenate all predicted tokens for the output sequence, as the greedy decoder does, you can end up with a situation where the output, instead of I am hungry, gives you I am, and so forth. You can see how this could be a problem, but not in all cases. For shorter sequences, it can be fine. But if you have many other words to consider, then knowing what's coming up next might help you better predict the next sequence. Another option is known as random sampling. What random sampling does is it provides probabilities for each word and sample accordingly for the next output. One of the problems with this is that it could be a little bit too random. A solution for this is to assign more weight to the words with higher probabilities and less weight to the others. You will see a method for doing this in just a few moments. In sampling, temperature is a parameter you can adjust to allow for more or less randomness in your predictions. It's measured on a scale of 0 to 1, indicating low to high randomness. Let's say you need your model to make careful, safe decisions about what to output. Then set your parameter lower and get the prediction equivalent of a very confident but rather boring person seated next to you at a dinner table. If you feel like taking more of a gamble, set your temperature a bit higher. This has the effect of making your network more excited, and you may get some pretty fun predictions. On the other hand, there will be probably a lot more mistakes.
You have seen in this video methods for sampling and decoding that will allow you to construct sentences using your model. However, these methods don't always produce the most convincing outputs. Instead, you will often get a very random set of words. In the next videos, you'll see two methods for sampling and decoding that tend to produce better results. Beam search is a technique that allows you to find the best sequences over a fixed window size known as the beam width. Since taking the output with the highest probability at each time step is not ideal, I will show you how to use beam search instead.
So far, the methods I've presented only consider word probabilities one at a time. These ways of sampling might not result in the highest probability sequences, and the sentences produced using these methods could not make sense. The overall most probable translation given an input sentence is not necessarily the most probable word at each step. For example, it's possible that choosing the most probable word at the start of the sequence could lead to a worse translation compared to choosing another word. If you had infinite computational power, you could calculate the probabilities of every possible output sentence and choose the best one. In the real world, we use beam search. This method attempts to find the most likely output sentence by choosing some number of best sequences based on conditional probabilities at each time step. Now, at each time step with beam search, you have to calculate the probability of potential sequences given the output of the previous time step. To avoid computing the probability for every possible sequence, you have parameter b, called the beam width. At each step, you only keep the b most probable sequences and drop all others. You generate a new word until all b most probable sentences end with the EOS token. So beam search consumes a lot of memory and could be computationally costly depending on your choice for b. As an interesting side note, greedy decoding is just a particular case of beam search where you set the beam width b to be equal to 1. To illustrate this method, consider a small vocabulary consisting of the words I am hungry and an end of sentence token. And let's say the beam width b is equal to 2. As with the other methods, beam search starts with a start of sentence token and gets the probabilities for the first word in the sequence. Here, I has a probability of 0.5, am has a probability of 0.4, and hungry has a probability of 0.1, and then EOS is at 0. Since the beam width is 2, you keep the two highest probabilities, I and M. Then, you calculate the conditional probability of all other words given the two sequences that you have kept so far, I and M. Given the word I, the model returns M with a probability of 0.5, and hungry with 0.3. Given the word M, the model returns the probability of word I with a probability of 0.7, and hungry with a probability of 0.2. These are the two conditional probabilities given the two previous sequences of P, of word 2 given word 1. Next, you calculate the probability by multiplying the conditional probability for 2 given the word I with the probability of word I. For instance, if the sequence of I has a probability of 0.5 times 0.1, this is equal to 0.05. The sequence IM has a probability of 0.5 times 0.5, which is equal to 0.25. You have to do the same with the sequences starting with the word M. Here the sequence MI has a probability of 0.4 times 0.7, which is equal to 0.28. At this point, there are 8 possible sequences, but with the beam width b equal to 2, you only keep the two sequences with the highest probabilities. So you keep the sequence IM and MI, and drop all others. Then for the next step, you use M as the input word to get the conditional probabilities for the IM sequence and I for the MI sequence. You repeat the process to calculate the joint probabilities and again choose the best sequence. This process stops when the model predicts an end of sentence token for all B most probable sequences. At the end, the sequence with the largest probability is chosen as the output. To get the conditional probabilities at each step, you have to use your model. For now, let's focus on the decoder parts of the model, ignoring the encoder and attention mechanism. At the start of the sequence, you will use your decoder to output a vector of probabilities for each of the words in the vocabulary. This is equivalent to computing the conditional probability of every word given the start of sequence token. Then, you select the most probable B outputs from the model and discard all other possibilities. After that, you use your model B times to find the conditional probabilities of all the words in the vocabulary, given the sequences that you kept in the previous step. Then, you compute the sequence probability and keep the B most probable sequences. And you keep doing this until the B most probable sequences gets to the end of the sequence token. Note that at each step, after the one where your sequence is only composed by the SOS token, you have to run your model B times. The vanilla version of beam search has some disadvantages. For instance, it penalizes the choice of long word sequences because the probability of a sequence is computed as the product of multiple conditional probabilities. However, you could normalize the probability of each sequence by its number of words to avoid this problem. Beam search also requires you to store the B most probable sequences and compute conditional probabilities given all of those sequences. Therefore, this method could be computationally expensive and consumes a lot of memory.
You have a new tool that you can add to your toolkit. Beam search has been widely used for quite a period of time and is still used a lot. In the next video, I will show you another technique that you can use, known as MBR, or minimum base risk. The main operation in Transformer is the scale dot product attention. You've already seen attention in the first week of this course. In this video, I'll remind you how it works.
First, I'll remind you of the formula used for scale dot product attention. Then you'll see some details about the math and the dimensions of the query's keys and values. Recall that in scale dot product attention, you have queries, keys, and values. The attention layer outputs context vectors for each query, and the context vectors are weighted sums of the values where the similarity between the queries and keys determines the weights assigned to each value. The softmax ensures that the weights add up to 1, and the division by the square root of the dimension of the key vectors is used to improve performance. The scale dot product attention mechanism is very efficient since it relies only on matrix multiplications and a softmax. Additionally, you could implement this attention mechanism to run on GPUs or TPUs to speed up training. To get the query key and value matrices, you must first transform the words in your sequences to word embeddings. Let's take the sentence, Je suis heureux, as the source for the queries. You'll need to get the embedding vector for the word je, then for the word suis, and finally for the word heureux. The query matrix will contain all of these embedding vectors as rows. Note that the matrix size is given by the size of the word embeddings and the length of the sequence. To get the key matrix, let's use a source of the sentence, I am happy. You'll get the embedding for each word in the sentence and stack them together to form the key matrix. You will generally use the same vectors used for the key matrix for the value matrix, but you could also transform them first. Note, however, that the number of vectors used to form the key and value matrix must be the same. Now you can revisit the scaled attention formula that I showed you before to get a sense of the dimensions of the matrices involved at every time step. First, you compute the matrix product between the query and the transpose of the key matrix. You scale it by the inverse of the square of the dimension of the key vectors, d sub k, and calculate the softmax. This computation will give you a matrix with the weights for each key per query. Therefore, the weight matrix will have a total number of elements equal to the number of queries times the number of keys. In that matrix, the third element in the second row would correspond to the weights assigned to the third key for the second query. After the computation of the weights matrix, you can multiply it with the value matrix to get a matrix that has rows and the context vector corresponding to each query. And the number of columns on this matrix is equal to the size of the value vectors, which is often the same as the embedding size. Scale dot product attention is the heart and soul of transformers. In general terms, this mechanism takes queries, keys, and values as matrices of embeddings. It is composed of just two matrix multiplications and a softmax function. Therefore, you could consider using GPUs and TPUs to speed up the training of models that rely on this mechanism.
Now you understand dot product attention very well. In the transformer decoder, we need an extended version called the self-masked attention. I'll teach you about it in the next video. You have learned all the basics of attention by now. In fact, you could already build a transformer from it. But if you want it to work really well, run fast and get very good results, you'll need one more thing, the multi-head attention. Let me show you what it is.
First, I'll share with you some intuition on multi-head attention. Afterwards, I'll show you the math behind it. Recall that you need word embeddings for the query, key, and value matrices in scale dot product attention. In multi-head attention, you apply in parallel the attention mechanism to multiple sets of these matrices that you can get by transforming the original embeddings. In multi-head attention, the number of times that you apply the attention mechanism is the number of heads in the model. For instance, you will need two sets of queries, keys, and values in a model with two heads. The first head would use a set of representations, and the second head would use a different set. In the transformer model, you get different representations by linearly transforming the original embeddings by using a set of matrices W superscript Q, K, V for each head in the model. Using different sets of representations allow your model to learn multiple relationships between the words from the query and key matrices. With that in mind, let me show you how multi-head attention works. The input to multi-head attention is the value, key, and query matrices. First, you transform each of these matrices into multiple vector spaces. As you saw previously, the number of transformations for each matrix is equal to the number of heads in the model. Then, you will apply the scale dot product attention mechanism to every set of value, key, and query transformations, where again, the number of sets is equal to the number of heads in the model. After that, you concatenate the results from each head in the model into a single matrix. Finally, you transform the resulting matrix to get the output context vectors. Note that every linear transformation in multi-head attention contains a set of learnable parameters. So let's go through every step in more detail. Say that you have two heads in your model. The inputs to the multi-head attention layer are the queries, keys, and values matrices. The number of columns in those matrices is equal to D submodel, which is the embedding size, and the number of rows is given by the number of words the sequences used to construct each matrix. The first step is to transform the queries, keys, and values using a set of matrices W superscript Q, K, and V per head of the model. This step will give you the different sets of representations that you use for the parallel attention mechanisms. The number of rows in the transformation matrices is equal to D submodel. The number of columns, D sub K, for the queries and keys transformation matrices, and the number of columns, D sub V, for W superscript V, are hyperparameters that you can choose. In the original transformer model, the author advises setting D sub K and D sub V equal to the dimension of the embeddings divided by the number of heads in the model. This choice of sizes would ensure that the computational cost of multi-head attention doesn't exceed by much the one for a single head attention. After getting the transformed values for the query, key, and value matrices per head, you can apply in parallel the attention mechanism. As a result, you get a matrix per head with the column dimensions equal to D sub V, and the number of rows in those matrices is the same as the number of rows in the query matrix. Then, you concatenate horizontally the matrices outputted by each attention head in the model. So you will get a matrix that has D sub V times the number of heads, columns. Then you apply a linear transformation, W superscript O, to the concatenated matrix. This linear transformation has columns equal to D submodel, and if you choose D sub V to be equal to the embedding size divided by the number of heads, the number of rows in this matrix would also be D submodel. Just as with single head attention, you will get a matrix with the context vectors of size D submodel for each of your original queries. That's it. For multi-head attention, you just need to apply the attention mechanism to multiple sets of representations for the queries, keys, and values. Then you concatenate the results from each attention computation to get a matrix that you linearly transform to get the context vectors for each original query. In this video, you learned how multi-head attention works, and you saw some of the dimensions of the parameter matrices involved in its calculations. You can implement multi-head attention to make computations in parallel, and with the proper choice of sizes for the transformation matrices, the total computational time is similar to the one of single-head attention.
In the last three videos, you learned about attention. You know the basic dots product attention, the causal one, and the multi-headed one. You're now ready to build your own transformer decoder. That's what we'll do in the next video. I'll show you a chronological order of when the models were discovered. We will also see the advantages and the disadvantages of each model. Let's start.
So this is a quick outline where you can see we start here with continuous bag of words model, then we got Elmo, then we got GPT, then we got BERT, and finally we ended up having T5 and so more. Like over here, you're going to end up having many more models coming up, hopefully soon. So this is not a complete history of all relevant models and research findings, but it's useful to see what problems arise with each model and what problems each model solves. So let's look at context over here. Let's say we have the word right, and ideally we want to see what this word means. So we can look at the context before it, and then we can also look at the context after it. And that's how we've been able to train word embeddings so far. So the continuous bag of words, over here you have the word right. And previously what you've been doing, you would take a fixed window, say 2 before and 2 after, or 3 or 4, whatever C is for the window size. And then you will take the corresponding words, feed them into a neural network, and predict the central word in this case, which is right. Now, the issue over here is that what if we wanted to look at not only the fixed window, but all the words before and all the words after? And how can we do that? So if we want more context, let's say we want they were on D over here. This is like the first left part of the sentence, and then all the right parts of the sentence. So instead of having the fixed window, we want to add like the street or history, for example. So to use all of the context words, what researchers have done, they explored the following using RNN. So they would use an RNN from the right and from the left, and then they would have a bidirectional LSTM, which is a version of a recurrent neural network. So you feed both of them in, and then you can predict the central word right. So that gives you the word embedding for the word right. Now, OpenAI GPT, what it did, so we had transformer, so the encoder decoder architecture that you're familiar with. And then we ended up having this GPT, which makes use of a decoder of stacks only. So in this case, we only have one decoder, but you can have several decoders in the picture. Elmo made use of RNNs or LSTMs, and we would use these models to predict the central word. So why not use a bidirectional model? So in this case, this is the transformer, and you can see that in the transformer over here, each word can peek at itself. So if we were to use it for on the right, you can only look at itself. But the issue is that you cannot peek forward. And remember, you've seen this in causal attention, where you don't look forward, you only look at the previous ones. So BERT came and helped us solve this problem. So this is a recap. Transformers encoder decoder, GPT makes use of decoders, and BERT makes use of encoders. So over here you have the legislature believed that they were on the blank side of history, so they changed the law. And over here we can make use of bidirectional encoder representation from transformers, and this will help us solve this issue. So this is an example of a transformer plus bidirectional context. So you feed this into your model, and then you get right and of. Because of this, you're able to look at the sentence from the beginning and from the end and make use of the context to predict the corresponding words. So if we were to look at words to sentences, meaning instead of trying to predict just the word, we'll try to predict what the next sentence is. So given the sentence over here, the legislators believed that they were on the right side of history. Is this the next sentence or is this the next sentence? So you have a sentence A, and then you try to predict the next sentence, sentence B. So in this case, it's obviously so they changed the law. So BERT pre-training tasks makes use of multi-mask language modeling. So the same thing that you've seen before, and it makes use of next sentence prediction. So it takes two sentences and it predicts whether it's a yes, meaning sentence 2 follows sentence 1, or sentence B follows sentence A, or not. So let's look at encoder versus encoder decoder. So over here you have the transformer, which had the encoder and the decoder stack, and then you had GPT, which just had decoder stack, and then BERT, just the encoder stack. So T5 tested the performance when using the encoder decoder, as in the original transformer model, and the researchers found that the model performed better when it contained both the encoder and the decoder stacks. So let's look at the multi task training strategy over here. So you have studying with deep learning.ai was it's being fed into the model and it gives you a 5-star rating. And hopefully it's a 5-star rating. And then you have a question, and then you get the answer. But the question here is, how do you make sure that the model knows which task it's performing in? Because you can feed in a review over here, and how do you know that it's not going to return an answer instead? How do you know it's going to return a rating? Or if you feed in a question, how do you know it's not going to return some, numerical output or some text version of a numerical output? So let's see how to do this. Over here is an example where, let's say you're trying to classify whether this is 5 stars or 4 stars or 3 stars. So you append the string classify, for example, and then it classifies it, and you get 5 stars. Let's say you want to summarize, so you add the string summarize : it goes into the model, it automatically identifies that you're trying to summarize, and it says that it was all right. You have a question, you append the question string, it knows that it's a question, and it returns the answer. Now, these might not be the exact tags that you'll find in the paper, but it gives you the overall sense of the idea. So in summary, you've seen the continuous bag of words model, which makes use of a fixed context window. You've seen Elmo, which makes use of a bidirectional LSTM. You've seen GPT, which is just a decoder stack, and you can see kind of unidirectional in context. Then you've seen BERT, which makes use of bidirectional encoder representation from the transformer, and it also makes use of multi-mask language modeling and next sentence prediction. And then you've seen the T5, which makes use of the encoder decoder stack and also makes use of mask and multitask training.
You have now seen an overview of the models. You have seen how the text-to-text model has a prefix. With the same model, you can solve several tasks. In the next video, we will be looking at the BERT model in more detail, also known as the bidirectional encoder representation for transformers. I'll now teach you about bidirectional encoder representations for transformers, or in short, just BERT. BERT is a model that makes use of the transformer, but it looks at the input from two directions. Let's dive in and see how this works.
Today you're going to learn about the BERT architecture, and then you're going to understand how BERT pre-training works and see what the inputs are and the outputs are. So what is BERT? BERT is the bidirectional encoder representation from transformers, and it makes use of transfer learning and pre-training. So how does this work? Usually starts with some input embedding, so E1, E2, all the way to some random number En. And then you go through some transformer blocks, as you can see here. So each blue circle is a transformer block, goes up furthermore, furthermore, and then you get your T1, T2, Tn. So basically there are two steps in BERT framework: pre-training and fine-tuning. And during pre-training, the model is trained on unlabeled data over different pre-training tasks, as you've already seen before. And for fine-tuning, the BERT model is first initialized with the pre-trained parameters, and all of the parameters are fine-tuned using labeled data from the downstream tasks. For example, in the figure over here, you get the corresponding embeddings, you run this through a few transformer blocks, and then you make the prediction. So we'll discuss some notation over here. So first of all, BERT is a multi-layer bidirectional transformer. It makes use of positional embeddings. And the famous model is BERT base, which has 12 layers or 12 transformer blocks, 12 attention heads, and 110 million parameters. And these new models that are coming out now, like GPT-3 and so forth, they have way, way more parameters and way, way more blocks and layers. So let's talk about pre-training. So before feeding the word sequences to the BERT model, we mask 15% of the words. And then the training data generator chooses 15% of these positions at random for prediction. And then if the ith token is chosen, we replace the ith token with 1, the mask token, 80% of the time. And then 2, a random token 10% of the time. And then 3, the unchanged ith token 10% of the time. So in this case, then TI, what you've seen in the previous slide, will be used to predict the original token with cross entropy loss. So in this case, this is known as the masked language model. And over here we have after school, Lucas does his blank in the library. So maybe work, maybe homework, one of these words that your BERT model is going to try to predict. And to do so, usually what you do, you just add a dense layer after the TI token and use it to classify after the encoder output. So you just multiply the output vectors by the embedding matrix, and then to transform them into vocabulary dimension, and you add a softmax at the end. So this is another sentence after school, Lucas does his homework in the library, and then after school, blank, his homework in the blank. So you have to predict Lucas does, and then library also. So in summary, you choose 15% of the tokens at random. You mask them 80% of the time, replace them with a random token 10% of the time, or keep as is 10% of the time. And then note that there could be multiple masked spans in a sentence, so you could mask several words in a same sentence. And in BERT, also next sentence prediction is also used when pre-training. So given two sentences, if it's true, it means the two sentences follow one another, otherwise they're different. They don't lie in the same sequence in the text.
You have now developed an intuition for this model. You have seen that BERT makes use of next sentence prediction and masked language modeling. This allows the model to have a general sense of the language. In the next video, I'm going to formalize this and show you the loss function for BERT. Please go on to the next video. I will be talking about the BERT objective. You'll see what you are trying to minimize. Specifically, I'll show you how you can combine word embeddings, sentence embeddings, and positional embeddings as inputs. Let's take a look at how you can do this.
So you're going to learn how BERT inputs are fed into the model and the different types of inputs and their structures. Then you're going to visualize the outputs. And finally, you're going to learn about the BERT objective. So formalizing the input, this is the BERT input representation. So you start with positional embedding. So they allow you to indicate the position in the sentence of the word. So where each word is in the corresponding sentence. So you have this. Then you have the segment embeddings, and they allow you to indicate whether it is sentence A or sentence B. Because remember, in BERT, you also use next sentence prediction. And then you have the token embeddings or the input embeddings. And you also have a CLS token, which is used to indicate the beginning of the sentence, and a SEP token, which is used to indicate the end of the sentence. And then what you do, you just take the sum of the token embeddings, the segmentation embeddings, and the position embeddings, and then you get your new inputs. So over here you can see you have masked sentence A, you have masked sentence B, they go into tokens, and then you have the CLS token, which is a special classification symbol added in front of every input. Then you have the SEP token, which is the special separator token. You convert them into the embeddings, so then you get your transformer blocks. And then you can see at the end, you get your T1 to Tn, your T1 prime to Tn prime. So these are each Ti embedding will be used to predict the masked word via a simple softmax. And you have this C also embedding, which can be used for next sentence prediction. So let's look at the BERT objective now. So for the multi-mask language model, use a cross-entropy loss to predict the word that's being masked or the words that are being masked. And then you add this to a binary loss for the next sentence prediction. So given the two sentences, do they follow one another or not? So in summary, you've seen the BERT objective and you've seen the model inputs and outputs.
In the next video, I will show you how you can fine-tune this pre-trained model. Specifically, I'll show you how you can use it to your own tasks for your own projects. Please go on to the next video. The T5 model could be used on several NLP tasks, and it also uses similar training strategy to BERT. Concretely, it makes use of transfer learning and masked language modeling. The T5 model also uses transformers when training. So let's take a look at how you can use this model in your own applications.
So you're going to understand how T5 works. Then you're going to recognize the different types of attention used and see an overview of the model architecture. So T5 transformer is known as the text-to-text transformer, and you can use it in classification. You can use it for question answering to answer a question. You can use it for machine translation. You can use it for summarization, and you can use it for sentiment. And there are other applications that you can use T5 for, but we'll focus on these for now. So the model architecture and the way the pre-training is done, first of all, is you have an original text, something like this, where you have, "Thank you for inviting me to your party last week." So you mask the certain words, so for inviting me last, and then you replace it with these tokens like brackets X, brackets Y. So brackets X corresponding to for inviting, and brackets Y corresponding to last. And your targets are going to be bracket X for inviting, brackets Y last. And these tokens or these brackets, like they keep going in increment order. So then it's bracket Z, then maybe bracket A, bracket B, and so forth. So each bracket corresponds to a certain target. The model architecture and the different transformer architecture variants that we're going to consider for the attention part here. So we start with the basic encoder decoder representation. So you can see over here you have fully visible attention in the encoder, and then causal attention in the decoder, and then you have the general encoder decoder representation. Just as a notation, so light gray lines correspond to causal masking and dark gray lines correspond to the fully visible masking. So on the left, as I said again, it's the standard encoder decoder architecture. In the middle over here, what we have the language model, which consists of a single transformer layer stack, and it's being fed the concatenation of the inputs and the target. So it uses causal masking throughout, as you can see, because they're all gray lines. And you have x1 going inside over here, get its x2, x2 goes into the model, x3, and so forth. Now, over here to the right, we have prefix language model, which corresponds to allowing fully visible masking over the inputs, as you can see here in the dark arrows, and then causal masking in the rest. So as you can see over here, it's doing causal masking. So the model architecture, it uses encoder decoder stack. It has 12 transformer blocks each. So you can think of it as a dozen eggs, and then 220 million parameters. So in summary, you've seen prefix language model attention, you've seen the model architecture for T5, and you've seen how the pre-training is done similar to BERT, but we just use masked language modeling here.
You now have an overview of the transformer model. You know how to train it, and you've seen that you can use it on multiple tasks. In the next video, I'll be talking about a few training strategies for this model. See you there! I will show you one of the most commonly used benchmarks in natural language processing. Specifically, you'll learn about the glue benchmark. This is used to train, evaluate, analyze NLP tasks. Let's take a look at this in some more detail.
So the GLUE benchmark stands for General Language Understanding Evaluation, and it is basically a collection that is used to train, evaluate, analyze natural language understanding systems. It has a lot of data sets, and each data set has several genres, and they're of different sizes and different difficulties. Some of them are, for example, used for coreference resolution. Others are just used for simple sentiment analysis. Others are used for question answering, and so forth. And it is used with a leaderboard, so people can use the data sets and see how well their models perform compared to others. So the tasks evaluated on could be, for example, sentence grammatical or not. For example, if a sentence makes sense or it does not. It could be used on sentiment. It could be used to paraphrase some text. It could be used on similarity, on question duplicates, whether a question is answerable or not, whether it's a contradiction, whether it's entailment, and also for the Winograd schema, which is basically trying to identify whether a pronoun refers to a certain noun or to another noun. So it's used to drive research. As I said, that researchers usually use the glue as a benchmark. It is also model agnostic, so it doesn't matter which model you use. Just evaluate on glue and see how well your model performs. And finally, it allows you to make use of transfer learning because you have access to several data sets and you can learn certain things from different data sets that will help you evaluate on a completely new data set within Glue.
You now know not only how to implement state-of-the-art models, but you also know how to evaluate them. In the next video, I'll be talking about question answering, and I'll show you how you can use these models to build a sophisticated QA system. I'll see you there.
Great work finishing this week, and especially the whole course! You will now take what you learned and code it up in this week's assignment. You will use a pre-trained model for inference and understand how the text-to-text transfer transformers, or T5 model, works. Note that a lot of these latest state-of-the-art models could perform several tasks on the same model just by altering the input. This allows for transfer learning and ends up giving some very good results. Good luck in the programming assignment.